Hitting 0 divided by 0 in a calculus limit means watching a race. Two distinct functions shrink simultaneously, crashing into the origin at specific speeds. Standard algebra fails at this boundary. Division requires a non-zero denominator to yield a defined value. When the numerator and the denominator both vanish, the rules of basic arithmetic cannot evaluate which zero is stronger. This graph shows exactly what is happening. Two distinct curves, f of x and g of x, drop toward the origin. The final value of this fraction depends on their relative rates of change. If f of x dives faster, the limit is 0. If g of x dives faster, it approaches infinity. To navigate this specific intersection, calculus relies on L'Hopital's rule. The theorem bypasses the undefined fraction by substituting a ratio of functions with a ratio of their derivatives. This relies on a strict geometric claim about how the trajectory of a function dictates its position. To legally substitute derivatives in place of original values, we require a mathematical structure that explicitly links a function's position to its slope. The standard mean value theorem does this for a single perv. It guarantees that over a smooth interval, there is at least one point where the instantaneous rate of change matches the average rate of change. Cauchy's generalized mean value theorem plots a parametric curve, comparing g of x directly against f of x. The secant line represents the average ratio. A parallel tangent line represents the exact derivative ratio. As the interval shrinks, these lines and their slopes perfectly converge. Because these slopes lock together at the limit, Cauchy's theorem provides the rigorous justification to evaluate the ratio of functions by calculating the ratio of their derivatives. Walter Rudin's Principles of Mathematical Analysis structures the formal proof of this rule in Theorem 5.13. The text establishes strict constraints before any algebra begins. Both functions must be strictly real-valued and differentiable over the interval approaching the limit. Additionally, the derivative of the denominator cannot equal 0 anywhere in that same interval. This prevents a secondary division by 0 error during the calculation. Finally, the theorem requires that the ratio of the derivatives approaches a distinct finite value, designated as a. By locking down these conditions, Rudin seals off any topological breaks. The functions are guaranteed to be smooth and continuous, setting the stage for the algebraic proof. This animated number line shows Rudin's initial algebraic setup. He plots the target limit a and then establishes arbitrary bounds, placing a variable r strictly greater than a. Because the ratio of the derivatives converges to a, there must exist some point c near the limit, where the ratio drops below r, trapping the derivatives beneath this upper bound. We then define a smaller interval between our limit point and c. Within this narrow window from x to y, the generalized mean value theorem guarantees a point t. This yields equation 18. The ratio of the original functions evaluated at x and y is exactly equal to the ratio of their derivatives evaluated at t. And because t is inside our trap, this entire expression is strictly less than r. The proof relies entirely on these inequalities. It physically boxes the function's ratio into a corner, restricting where it can possibly go as we approach the limit point. This diagram shows the final analytical maneuver. Looking at this fraction, Rudin instructs us to hold the variable y completely stationary, while we push x toward our limit point. By definition, as x approaches the limit, both f of x and g of x evaluate to 0. The terms vanish entirely. The remaining negative signs cancel out, leaving us with the ratio of f of y over g of y bounded by r. We can perform this same logic from the other direction to establish a lower bound. By systematically tightening those bounds, squeezing r closer to a, the ratio of the functions is forced to equal a. Rudin's construction demonstrates that the limit emerges directly from these topological bounds, leaving no room for any other value. To see the mechanics of this proof in action, we apply it to a classic limit, x minus the sine of x, all divided by x cubed, as x approaches 0. The mandatory first step is verifying the hypotheses. Plugging in 0 yields 0 in the numerator and 0 in the denominator. The indeterminate form is confirmed. This split screen tracks the calculation. On the left, taking the derivative of both sides gives us 1 minus cosine x over 3x squared. On the right, the function's graph smooths out slightly. However, plugging 0 into this new expression still yields 0 over 0. Because the new ratio remains indeterminate, we apply the rule recursively. Another derivative leaves sine of x over 6x, still indeterminate. A third derivative yields cosine of x over 6. The denominator is finally a constant, breaking the indeterminate loop and giving us a final limit of 1/6. Verifying the 0 over 0 state at each level is required. Applying this recursive technique to an expression that is not indeterminate violates the initial boundaries of the proof, yielding false mathematical conclusions. This rigorous logic holds perfectly for real numbers, but the entire theorem physically fails when transitioning into the complex plane. Walter Rudin provides a definitive counterexample. He defines f of x equal to x and g of x equal to x plus x squared times e to the power of I over x squared. As x approaches 0, this limit cleanly resolves to 1. This visualization shows the failure state when we calculate their derivatives. While f prime remains a constant 1, the derivative of g of x contains an oscillating term. As the vector approaches the origin in the complex plane, it spirals chaotically and never settles on a limit. The rule fails here because Cauchy's generalized mean value theorem requires strict real-valued inequalities to trap the limit. That mathematical trap physically does not exist for complex vector-valued functions. L'Hopital's rule provides a definitive pathway through indeterminate limits, provided the underlying real number foundations of the mean value theorem remain intact. Subscribe for more rigorous deconstructions of higher math.